Hello, this is the presentation for the Senior Design course, Civi 495. We will be presenting our project, the Concrete Canoe. The name of our canoe is El Luchador, and we are the 2014 AACE Concrete Canoe team. My name is Raul Sierra, and I am the project manager.
Hi, my name is Joey Fallon, and I was responsible for the whole design for this year's Concrete Canoe.
My name is William O'Gorman, and I am in charge of the concrete mix design.
Hi, my name is Kevin Anoob, and I am in charge of the structural analysis.
Hi, I'm Anthony Salvani.
And I'm Ramsey DeCastro.
And we are the construction leads.
Here's a quick outline on what we plan to present. I will give a quick overview of the structure of the team, followed by a description of our plans and goals that were set at the beginning of the semester. The design team will present the research and design, followed by the construction team's influence with the design and development of the construction methods and areas where we can improve on. Lastly, I will present my work as PM and a conclusion. The team was broken down into 3 tiers: project management, design, and construction. Project management position was held by a single person and was in charge of the design team, which consisted of hull, mix, and structural design, as well as managing the construction team. At the beginning of the semester, we established certain goals to be achieved by the end of the design class. These goals were: design of lightweight concrete mix, introduce new reinforcement methods, develop a new casting method, cast a canoe before the end of the course, and design a new hull. And now here is William O'Gorman with the mix design.
The primary goals for this year's concrete canoe mix were to create a lightweight mix that could be easily spread onto a tile cutout and placed vertically on a mill mold. Several base requirements were set from the start, including a density less than 60 pounds per cubic feet, both in order to float and remain competitive, a 1,100 psi compressive strength, fiber reinforced to increase tensile and bending strength, air entrained to reduce unit weight, and enhance the resistance against sulfate, since the races would be held in Mission Bay. Over 30 mixes were developed and tested over a 2-month design period before arriving at our final mix. The final mix consisted of Type 2-5 Portland cement to increase resistance against sulfate, Class F fly ash and silica fume for their lower density compared to cement and finer particle size, which reduces permeability, leading to decreased weight in the water and further increases sulfate resistance. Nikon PV RCS 15 fibers are used to chemically bond with cement to increase tensile and bending strength and reduce shrinkage cracks. Pour over glass beads and 3MK 20 glass microspheres were used to provide lightweight aggregate. For our admixtures, we used Acryl 60 as a polymer modifier, Glanium 3400 NV as a high-range water reducer, Riotech Z60 as a workability retainer, and Riomac VMA 362 as a viscosity modifier. Our final concrete mix achieved a unit weight of 55 pounds per cubic feet, an air content of 15%, and a 28-day compressive strength of 1,650 psi. Compared to SDIC's concrete canoe mix last year, the unit weight has been reduced from 80 to 55 pounds per cubic feet, which represents a 30% decrease while still maintaining sufficient strength. This drastic decrease in density will produce a lighter canoe that will help propel SDSU in the first place.
And now here is Joey Fallon with the whole design.
The process began with looking at all the various aspects that go into the design of a canoe. Once we had decided as a team on what we wanted as far as the performance of this year's boat, I began creating the preliminary design. For the outline of the canoe, we went with an asymmetric shape with the widest point 12 inches after the center of the vessel. This allows for a sharper entry line, which improves the hull's efficiency and tracking capabilities. For the cross-sectional shape of our hull, we went with a shallow arc design. Through research, it was determined that this was the most versatile profile, providing a good balance between initial and final stability, as well as being efficient for paddling and maintaining speed. We increased the overall length of this year's canoe to 21 feet compared to last year's length of 20 feet. Longer canoes are faster, track in a straighter line, and provide more carrying capacity. The trade-off with a longer canoe is decreased maneuverability, but we were able to compensate for that with other design implementations. We elected to decrease the maximum width of this year's canoe to 30 inches from the previous year's design of 31.25 inches. Decreasing the overall width to 30 inches helped streamline the shape of the hull, but not so much that the canoe would become unstable for paddling. To improve the maneuverability of our longer canoe, rocker was incorporated into the bow and stern of the vessel. A total of 4 inches of rocker was added to the stern and 5 inches of rocker in the bow. Adding the rocker to the canoe reduces the submerged profile of the hull, which allows the quick execution of turns by allowing the water to flow laterally underneath the canoe. The entire design was carried out using SolidWorks. This helped with being able to perform some of the hydrodynamic as well as structural analysis of the design. However, because I had no previous experience using the software and there was a steeper than expected learning curve, the finalization of my design was slightly later than what we had scheduled. Fortunately, due to good project planning by our project manager, it didn't lead to any major holdups in the overall progress of the project.
Now here is Kevin Anoob with the structural analysis.
The first thing I did was took Joey's SolidWorks model and ran it through SolidWorks finite element analysis software, adding in the expected loads from the paddlers, the buoyancy force from the water, and the material properties from Billy's concrete mix. From this, I was able to get the expected deflections, stress concentrations, and effective weak spots of the canoe. After researching different types of material and meshes, I chose a carbon fiber wire mesh as our primary reinforcement because it's very lightweight, its tensile strength is 290,000 psi, which is more than 4 times larger than steel, and because it is designed by the manufacturer to bond well with concrete. I also decided to use an additional steel cables as reinforcement, along with our carbon fiber mesh, in order to implement a pre-stressing system on our canoe. After that, I went about designing our reinforcement scheme through hand calculations. I used reinforced concrete analysis and treated the canoe as a simply supported, uniform beam with the cross-section of a U-shape. I analyzed 2 different loading cases, one with 4 paddlers in the canoe spread out equally, and one with 2 paddlers, one on each end of the canoe. Using the maximum moments that the canoe would experience in each scenario, I found the required amount of reinforcement we need and iterated different combinations to find that we would use 1 layer of reinforcement mesh and 6 cables of pre-stressed steel cables, running longitudinal to the canoe, 4 on the bottom and 1 on each of the sidewalls. Lastly, I used pre-stressed design calculations to find the force being put in our cables. By comparing 4 inequalities that describe the allowable compressive and tensile strength at transfer of the pre-stress and in service, I got an acceptable range of forces to use for our cables, which was chosen to be 200 pounds for each, 1,200 pounds total of pre-stress on our canoe. By implementing pre-stress to our canoe, we are increasing the bending moment capacity, making our canoe more efficient. It also makes our canoe more crack resistant since our canoe is in constant compression, which makes less imperfections in our final canoe. By pre-stressing our canoe, we gain an edge in the competition to help propel us to first place.
Finally, we have the construction team.
Construction is the actual building. It makes a reality of the idea of conception and the plan of design. Being on the construction team, both Ramsey and myself had a few goals that we set in order to minimize the construction error during pour day and in order to make the canoe come to life. One of our first goals was to come up with a way to incorporate pre-stressed steel cable, since that was one of the chosen reinforcements of the structural design. Also, since the hull was designed to have a thickness of 0.5 inches, developing a method to lay on the concrete in a uniform fashion was essential. And lastly, we needed to make sure our construction process was as flawless as we can get. We understand that there will always be some sort of error or unforeseen problems that may arise, especially dealing with construction. So we made it a point to come up with a construction process that will minimize any sort of patchwork needed after the day of the pour. Ramsey will now go over the different challenges that we had to overcome during initial planning and implementation.
Thanks, Anthony. Well, like all goals, we of course had our challenges. Cold joining between layers of concrete is definitely something we had to be aware of. Failing to have properly bonded concrete will result in our canoe to not be as structurally sound as designed. Since pre-stressing was something we decided was necessary for the canoe, we had to develop a rig or system that could withstand the necessary pounds of force. Another challenge for the construction team was to work closely with what the designers had cooking up in order to make sure that the design was constructionally feasible. Finally, prior concrete canoe pour days indicated the lack of standard procedures and safety measures. It is important for any construction projects to follow safe construction habits and BMP-style outline to ensure the safety of our construction volunteers and environment. To ensure safety, we have developed the Task Hazard Controls checklist with the help of DN Tanks, a local concrete tank business, and a large concrete canoe sponsor.
Our overall goal was to create a completed workbench that included the platform for the concrete form, pre-stressed rigs, and hydration system. We began working towards this goal by first designing and fabricating what we call our stress boxes. These boxes were made out of 1.5 by 1.5 inch steel tubing and 24 gauge hot rolled steel plates. The tubing and plates were welded together and steel legs were bolted on the ends for support. These boxes were constructed to withstand the over 1,000 pounds of force running through the cables. In order to work with the design of the mix and chosen reinforcement schemes, the decision of constructing the canoe by use of a male plug was chosen as our concrete form. The male plug allowed us to run the pre-stressed cables within the walls of the canoe without having to drill extra holes into the form. The form was created by connecting 61 individual cross-sections cut out of foam by use of a water jet. Once all the pieces were connected, Sanding was then done in order to get the shape that we wanted.
Last year's concrete canoe workbench was created to hold a self-consolidating male and female mold. This bench was immovable, its location was crammed, and was not suitable for our construction goals. Our team went to work, redesigned, and retrofitted the 22-foot-long bench to save time and money. We first deconstructed many of the bench's features that held the previous female mold. By constructing a new tabletop and installing 6 4-inch rolling wheels, our bench was able to hold our new male form stress box rig and allowed our workbench to be moved into a larger construction area. Our hydration system was designed to hydrate the concrete canoe in its entirety. It was designed using half-inch PVC pipe, rubber hoses, and 12 misters. These misters worked simultaneously to saturate the concrete. The runoff of the hydration was taken account of and was captured by our customized tabletop and drained into buckets. This water was then reused in the hydration with handheld misters.
As project manager, I was responsible of creating a project schedule for the team, leading weekly update meetings, in charge of distributing members to work on tasks that they were not directly responsible for, and I was also the lead in the Capstone class. As project manager, there were several milestones that the team needed to complete in order to accomplish our goal of constructing the canoe by the end of the semester. Some of these milestones were finalizing the hull design, the construction of the hull, finalizing concrete mix, determination of the structural reinforcement, practicing casting methods, and lastly, reach the deadline for the first scheduled pour. As Joey previously mentioned, the hull design was behind schedule 9 days. The construction of the hull was behind schedule 2 weeks because the team never verified the thickness of our foam blocks before cutting them, resulting in an extra step to cut the foam blocks to the required thickness. By increasing the working hours of the entire team and working around the clock, these setbacks were mitigated and didn't affect the day of the scheduled pour. The determination of the structural reinforcement was also behind schedule 17 days due to the delay with the hull design and also because there was a slower than anticipated learning curve. Fortunately, this task was scheduled to be completed several weeks before the pour day. The design of the concrete mix was finished ahead of schedule, which helped to have more casting practices by the team. There are several challenges we faced during the course, but we were able to overcome these challenges with proper planning, distribution of work, and overall good communication within the team. All our goals were reached. There are still areas open for improvement for our next pour to construct a winning canoe. Thank you for your time, and if you have time, check out our website for further updates on the competition and our next pour.
I believe.
I believe.
I believe that.
I believe that.
I believe that we.
I believe that we will win. 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 I believe that we will win.
I believe that we will win.
I believe that we will win. I believe that